my talk today. Okay. The title of my talk today is the network performance model and the importance identification. It's a case study of a private car in Zhengzhou city. This is a joint work with a master student in our group, Chenlan WANG, and Zhang Xiaotian. And my talk will for the 5 parts. The first is the introduction, then data and descriptive analysis, our new efficiency measuring model and the results, and finally the conclusion and limitation. So first, so with the economic growth and urbanization, vehicle numbers increases very rapidly in last decades, which causes traffic congestion and network inefficiency. So the city that Zhengzhou, the data we use in this study, the capital of Henan province, the private car ownership reaches over 2.8 million at the end of 2017, and this accounts for over 90% of the car ownership in the whole city. So averagely, every 100 households owns 56.8 cars in that city. So the picture on the left is a morning peak. Commuters usually have to experience congestion all the way to work. And on the right, it is a picture that we have from a navigation map app. The red line shows the congestion links. So this maybe we can usually see such kind of pictures from our phone. So such app can collect real-time GPS data and show us visible information of how much vehicles on the road now. So when we see the red, we know that it is congested. So the speed is very low, but we do not know how this congestion comes. So where are these vehicles from and where are they going? So the OD analysis would help us to understand the basic demand. And this will help us to judge in which case the road situation would be better and provide policy suggestions for inducing the demand source. A second thing, when we see the red, you usually think that there are many vehicles. But it is just because the road capacity is too small or the network is a lack of coordination. So if it is a lack of coordination, we say the system is inefficient. So congestion is not equal to inefficiency. So why? But the construction of the urban road network actually in China are basically completed. At least in many large cities are completed. So the implementation of traffic improvement measures will face a greater psychology and economic risks when implementing the improvement measures. So it is important to quantitatively to measure the network efficiency and to know how much the system can be improved by such by different kinds of demand coordination. So as we said, the measuring the OD level and the citywide efficiency is helpful for managers to improve the transportation planning, but it just may not realistic to improve the efficiency for all OD pairs of the whole city. So we need to it is more reasonable to allocate a limited budget or resources on selected ODPs, but how to select them, how to assign the resources. From the system perspective, it may not wise to induce the demand for the most inefficient ODPs directly. So just like that we do in playing the pool, we usually do not kick the ball that's closest to the pocket. We need to calculate the angle and the spin, and to think about the response of all balls. So I hope to have one to more than one pot than by just one shot, right? So based on this, we need to think carefully and choose a point to kick. So in the traffic system, it's also important to identify the vital ODPLs or the key ODPLs affecting the system efficiency and when designing the traffic control measures. So here the vital means affecting the system the most. So then we can do the least coordination work and have the most improvement of the system. The existing work in the literature, we organize them into two streams. The first is a common used framework. It calls that excess commuting approach. It represents the additional commute at means how much the excess part of the actual cost that you use. So it is a ratio like that shown on the top of it. And we have many extensions like consider the maximum commute or the random commute. And the second stream is the transportation net efficiency. It's mirrors both the RD level and the citywide transportation efficiency by integrating the above EC framework. And our work is based on these two framework. The contribution of our work can be organized as the first our study first develop the existing mirrors and on the basis of the EC framework, and to measure the OD level and citywide travel efficiency. And we proposed a new index to further identify the vital ODPLs for the network improvement. We used the private car data in Zhengzhou to conduct both the assessment. From the experimental results of our study, we can see that the vital ODPL do not coincide the inefficient ODPLs. So from the system perspective, it is not wise, indeed, to induce the demand for the most inefficient ODPLs directly. We need to choose. And we also provide an analysis on the characteristics of these inefficiency ODPLs and to find the possible reasons of the vital inefficiencies from the perspective of land use. And the results of this paper can help us to further design more targeted traffic management measures and the urban land planning schemes to improve the efficiency of the network, of the traffic network. The second part is about the data. First, the Zhengzhou city. Okay, it is the capital of Henan province. In the map, it's around just in the center of China. The red point is the city, and it's it is 7,446 square kilometers in L and 90.88 million in population. So you can see that it is a very big city. The data collected is in the gray part in the below. It's a built-up area in with dense populations, and it consists of three parts. Area A is the main urban area within the belt freeway of the city. LB is Longhu town. It is a newly built-up area. And area C is the airport area. And our data is collected from the 5th Urban Comprehensive Transportation Survey of the Zhengzhou city. We have the specific OD information of private cars in the working days around 25 days data in 2017. We collected from over 30,000 households, and we have 105,000 trips in total. For each item, we have 4 attributes: the start time, the end time, the start location, and end location. So from the data, the trips counts over time. So we can easily see that there are 2 peaks. One is from 6 to 8 in the morning, and the other is from 17 to 19 in the evening. So we have we call them morning peak and evening peak respectively. And from the right side, we will focus on these two peaks. So we will just use this the data during these peak times. And the right is the distance distribution. You can see that the majority of the trips are over 2 kilometers. So we will use this in the next page. And here that is we can just have the geometric distance from the origin and the destination. We do not have the detailed path information of this from this data. So we use a path planning API of the AMAP to estimate the travel distance. So in order to simulate the real traffic condition faced by the driver, because the data happens in different times. So we want to simulate with a similar time. The travel distance was collected from the same time period on a parallel working day. So, for example, if the item, the data, the travel distance for the sample is between 8 to 9 a.m. on a Friday, and then we estimate the path planning by the path planning information on AMAP between the same time from 8 to 9 a.m. on another Friday. So we use this way to fill the path information. Then we do the traffic zone partition. We did it in 2 steps. Step 1, we first divide the main urban area into 26 medium-sized zones by urban expressways and the rivers. And the next step 2, we further divide the main urban area so that the inter-zone trips are within 10%. As we have shown in the previous slide, we said the majority trips are over 2 kilometers. So in the center, very center part, it's the length of the zone is about the length is about 2 kilometers. So like that. Then so the inter zone trips are within 10%. Then the spatial distribution. So we can see that the traffic flow is kind of tighter, right? So in the morning, that private cars gather in the downtown area in the morning and disperse from the downtown in the evening. Since the private cars account for most of the total trips in weekdays during the peak time, so the traffic flow in the Zhengzhou city have tighter characteristics, and the peak hour of weekdays is essential to improve the efficiency of the private car travel. Next is our model. First, the OD level model. So first, the efficiency of a single trip. We use the average speed of the trip between the origin and the destination, and we compute the ratio of the actual speed, average speed, and the maximum speed. And this is the first part. And the other part is about the distance. It is the ratio of the geometric distance and the route distance, and we combine these two as the efficiency to measure efficiency of a single trip. And for a typical OD pair, we use the average efficiency value of all the trips. So we sum all of the trips up and then divided by the number of trips. And the last, the OD efficiency the impedance, it's a kind of it is kind of a conversion, right? To make it to make it similar as the conversion measure of the cost. So from the efficiency, you can see it is as it is ratio, so it is less than 1. So the bigger the better. But usually, when we say cost, the cost we hope the cost as smaller as possible. So we use the implicant in equation 3. So we just to make it then the lambda here is a hyperparameter used to avoid the situation that the efficiency is 0, and then to make this part is not 0 or to go to an infinity. And this we will use is implicit very often lately. The city level, we use the EC framework, the exact commuting framework. Here that we use the ratio of the additional commute, which is the difference between the actual cost and the minimized cost. We use the ratio of this its difference and the actual cost. So the EC value represents a proportion, actually the proportion of the excess cost of the actual cost. The high EC value means high cost exists in the system and the low system efficiency. So this traditional EC calculation is cost-based. The EC value under different cost units can be obtained by changing the cost unit into the driving distance or driving time, or any combined cost. We will use this framework by replacing the cost unit with the implement that we just defined last slide to measure the efficiency of the whole city. And the meaning of the linear programming here is that to just imagine that the region is redistributed, the flow is redistributed, so as the total cost, the travel cost of the whole city is minimized. And the vital ODPLs or ODPLs. So as we said before, the optimizing the inefficient ODPL directly may not effectively improve the traffic demand efficiency values at the whole city level. So it is important to identify the vital ODPLs affecting the system efficiency when design the transport control measures. Here that the total travel cost of the entire city is defined as this is the cost and times all of the demand here, and sum them up. So, but here we also introduce another a new cost is the total travel cost in the absence of the single ODPL. So we exclude this typical ODPL out of the system and then calculate the cost again to find what would happen if the ODPL, the demand is excluded. And we also calculate the minimum total travel cost in the absence of this ODPL when the demand is excluded. What will happen like this, and we do the linear programming again. Then the EC values are in the absence of the ODPL. So it is also the excess cost, but in the new situation that but on this basis we define the importance index, which is the difference of the excess cost of the when this typical ODPL is in or out of the system, and calculate the ratio of it. So we can see the defined importance index can be positive or negative. The positive means that the value of the EC goes down and the system efficiency is improved. Then this ODPL is excluded. And the negative is the other case that the EC value rises and the system efficiency gets worse when the ODPL is excluded. So the higher the absolute value of it is, the more of the specific ODPL would affect the efficiency of the whole city. So next is our result. First, we calculate the efficiency values for all the ODPLs. There are around 1,500 ODPLs in the network, and we find that the top 10% ODPLs are with longer geometric distance and longer route distance. It means that vehicles traveling longer distance are more likely to travel more efficiently. And the distance ratio here of the high efficiency ODPLs is very high, which is at about 0.95 at average. So this means that these vehicles are nearly traveling along straight route between these ODPLs, and is very efficient. And the distance ratio of the bottom 10% ODPLs are relatively low. It's at 0.28 at average, which means that the vehicles may detour during the traveling. The spatial distribution of these top 3% and the bottom 3% of the ODPLs. The high efficiency ODPLs most expand and extend beyond the third ring road, which is the blue part on the left. So you can see the lines here. This high efficiency often associated with long distance, you can see, and the low efficiency ODPLs are mostly distributed within the three ring road, the blue part. So the drivers may experience intersections, right, and traffic signals more frequently in the city center. So this will pull down the trip efficiency. While the long-distance trips are more likely to use freeways and attain higher average travel speed. So this means the city center is usually more congested, and the trip have to take more driving time, even though their traveling distance is very short. So this may be inefficient in the city center. The citywide efficiency, which is that we have such a table. We can see that the EC values are 33%, 51%, and 49% under a different cost units of travel time, travel distance, and the combined one of implements. So you can see that this means that there are quite a room for our improvement. And the spatial distribution of our optimal OD flows. This slide shows the ideal case that if we redistribute all of the OD amounts, you can see that and the thickness of the line connecting the OD pairs represents the traffic volume. And you can see that the left two, part A and part B, the spatial distribution are quite similar, right? And but the possible reason may be that there is a possible correlation between the travel time and the travel distance. And the part C, it is the combined one, and the spatial distribution looks quite different. And this page shows that how the OD flow should how would be organized to be the most efficiently with different cost units. This is the ideal case. And next, we did a coefficient analysis between these three cost units: the distance, the speed, and the distance, speed, and the implement. EIMP. You can see that the speed and the EIMP, there is a strong negative correlation between the speed and the EIMP. And the distance and the EIMP, there seems no significant negative correlation between these two in all the OD pairs. But in the top 10% OD pairs, the most efficient ones, we say that the distance factor is positively correlated with the EIMP. This means that this may be due to the fact that some drivers take a detour and to avoid congestion. So, and there are a similar work actually. They use the data in New York, but that work didn't show the obvious correlation with between the distance and the efficiency of the taxi driver. But they use that data they used from the taxi data. But here in this study, we use the private car data. So the possible reason may be the taxi drivers have less concern about the driving distance than than the private car drivers when choosing a route. By choosing a route. Lost the speed and the distance. There is a weak negative correlation between the two factors. So this means that when the distance factor is low, the driver are more likely to get a higher speed factor. And this is consistent with the fact that the drivers usually have a detour to avoid some congested roads and thus get a higher speed. So this is consistent with our real world. The vital OD pairs, we use them our new index of importance to calculate it. You can see that we have these three pictures under different cost units. Part A for travel time, part B for travel distance, and part C for the EIMP. We can see that the values of the importance can be positive or negative. And the positive means that when the OD pair is missing, the EC values decreased, and the private car traffic network efficiency is improved. So we can from the picture, we can see that the positive importance values and the negative are roughly half and half. So and we also calculate the correlation index of the efficiency and the importance. We find is very low. Is around it is 0.075. So there's no significant correlation between the efficiency and the importance of a single OG pair. So this shows that the direct improving the inefficient OD pairs may not a good way to improve the efficiency of the entire network. So it will be more effective to alternatively improve the vital OD pairs. Thus, it would be good to if we can identify the vital ones. The spatial distribution of the top 5% OD pairs with positive importance values. You can see that the spatial distribution in picture A and B are quite similar. The same. One is picture A is for travel time, and B is for travel distance. We can also see some kind of correlation between these two. So the spatial are quite similar, and But the combined unit of EIMP, the distribution varies greatly. It looks very different. As we have said that the vital ones and the inefficient ones are not coincide, but we can still have some that's the both vital and inefficient. So here that we rank the top 10 important OD pairs here, and you can find some of them here. We list five. Five ones are also inefficient, with the bottom 10% inefficient. So the five ones are the number here is actually the number of the zone here is 2215, and the last four we have actually two pairs of OD pairs. It's here. Next, we will further discuss these three pairs, right? To discuss the inefficiency reasons of these zones with the land use information of the Zhengzhou city. Here first is the zone 22 and 15. Here we have the values of the functional land rate here. This means the land area of a specific function corresponds to each unit of residential land in the zone. Here we can see that zone 22 has significantly more commercial and financial land, and zone 15 are mainly residential used. So we can see that a large volume of commuting demand would flow out during the morning peak hours and return during the evening peak hours. This would easily cause congestion during these two peak periods. Second pair, zone 20 and 13. 20, this part has significantly more commercial and financial land, education land, and green space, while zone 13 are mainly residential areas. So due to the large number of residents and few schools in zone 13, so people need to send their children to school in zone 20 during the peak hour. This would is likely to induce low traffic travel efficiency. The last is zone 28 and 29. Zone 29 contains a large volume of manufacturing plants and education land. So this may attract large commuting flows during peak hours and cause traffic congestions. So from the above, we can see that these inefficient OD zones are often with dense residentials or where schools are commercial and manufacturing plants located. So this we can see with the land use information. Finally, we come to the conclusion. So this study, we developed existing models on the basis of the EC framework to measure the efficiency of the Zhengzhou city, and we propose a new importance index to help us to identify the vital OD pairs for network improvement. Second, we did the assessment with the private car data in the Zhengzhou city, and we considered three different cost units of travel time, travel distance, and the ingredient unit of EIMP. The spatial distribution and the efficient and inefficient OD pairs are illustrated with map for practice insights. We also did some correlation analysis and to find that the factor of speed has more impact on efficiency compared to the distance factor. Third, we also quantify the importance level of the order pairs, and to analysis with the land use information, and we find that the inefficient OD zones are often with dense residential or where the schools, commercial, and manufacturing plants located. We also have some limitations. So first, we only use the private car survey data, but it would be may provide more insightful, and if we combine with public transportation data. So as actually the public transportation will have an impact on residents' travel behavior and consequently on the traffic natural efficiency of the private car. Second, this study doesn't involve the specific road segment sections. We only use the information of the orange and the destination. So all those inefficient vital OD pairs are given in this article. So the planners may be more concerned about specific road segments, and this would be more interesting if we have relatively more specific data. The third, when exploring the reasons for the vital inefficient OD pairs, we speculate the travel purpose of each zone just through the land use information. This will inevitably cause some errors. Of course, this is what is in my talk. Thanks for the listening. I'm happy to answer any questions.